All right, this is Final Control Elements Lab 9. What we're going to do today is we are going to integrate a drive with a PLC. This is the drive that we're dealing with, this PowerFlex 525 drive. Last week we got it wired up initially, got it set up initially, got the parameters set to what we want in Connected Components Workbench, and we were able to do all that. The big downfall to where we left it off last week was the only way to actually run this drive and use this drive was you had to come up here to the actual panel, the faceplate here, and make changes and actually run it and change the speed that way. So what we're going to do this week is we're going to integrate it into a PLC. And so we'll show you how all that gets done. And this is the initial wiring diagram that we're that we're using. Okay, what we have here is our two rails for a line diagram. Power coming in, L1 as our black wire here. Okay, that comes in underneath this cover. Down here we have power coming in here, which is shown going into L1 and L2 on the drive. That's incoming power going into the drive, and then your outgoing power from the drive goes to the motor, and T1, T2, and T3. That's underneath that cover there, and that's all already been done from the last lab. That all stays the same. The drive and the motor get powered up and stay the same. Everything we're dealing with is going to be on this controls side this week. Okay, this here is left over from last week. This is our R1, R2 relay going into the light. So whenever the motor is running, the light comes on. That's shown in our line diagram right here. R1 and R2 going into light. So what happens is whenever the relay closes, because the drive is on, this relay R1, R2 is inside the drive, and whenever the drive is running, it closes the relay. Whenever that relay closes, we get 110 volts going from here all the way through this relay contact. This relay contact here closes, allowing power to go into the light and the light to come on. Everything else for our controls for this drive is going to be running on 24 volt DC. Now, the good thing about this drive that most drives will have is they'll actually have a 24 volt power supply built right into them. And this one happens to get 24 volts coming off of terminal number 11, and you can see that in your wiring diagram right here. This terminal number 11 is plus 24 volts. Okay, and so what we do with that is we bring it down here, comes down, and it goes into the selector switch. And we'll talk about what that selector switch does a little bit later. And so it goes down into that selector switch. These other terminals here, 13, 14, and 2 and 4, are our remote signals. Okay. Everything before, what we did is we put it on and we controlled it from the faceplate. So we didn't really need any of these other signals coming in here. These are all digital signals, in this case, and an analog signal down here that's going to come from a secondary source. Our secondary source happens to be a PLC. Okay. Could be a couple of other things, but a common way that we're going to do it is a PLC. The primary source is the faceplate up here. Okay, what we set up is in Connected Components Workbench last week that our digital input coming into the drive, number 5, okay, digital terminal block, digital input, DIGN, digital input terminal block number 5 is going to be our speed in our start source number 2. Okay, so our speed in our start source number 1 is what's coming in on the faceplate. Okay, the buttons and the potentiometer on the faceplate. Number 2 is going to be our remote, okay, which is going to come from the PLC. Now, where that comes in is also shown here. Digital input terminal block 2 comes in here. Speed reference to 0 to 10 volt input is shown here as well. Okay, so we tell the drive what we're going to be doing in here in this software and then we wire it up accordingly. So what does all that mean? Let me bring down this picture here to show you a little bit more up close of what's going on here. What we have here is R1 and R2 is still the pilot light. So that relay closes whenever the drive comes on to turn on the pilot light. The difference that we have here is all this other stuff inside here. Okay, and so what we have is number 11 and number 5, terminals 11 and 5. 11 is plus 24 volts. Okay, so that's just plus 24 volts come off of terminal 11 all the time. And then where this goes to is it goes to our selector switch down here. Okay, and that is shown on this wire right here. It goes down to our selector switch. It's shown on the wiring diagram right here. So when this selector switch is open, and when it's in the off position or the left position, the local position, that means we do not have 24 volts plus 24 volts DC on digital contact this terminal block number 5. Okay, so this wire here does not see 24 volts. 24 volts does not go in this wire. When this does not have 24 volts on it, that means that the drive should be looking for speed and start source number 1, which again is on the faceplate. Once it sees 24 volts DC coming onto it, if we turn this switch on, now it should not look for a start and a speed source number 1. It should look for start and speed source number 2. Okay, start and speed source number 2 is going to be coming from these inputs here for these wires. Okay, speed signal comes into terminals 13 and 14, which is down here. That's a 0 to 10 volt signal coming in from our analog output of our PLC. And then number 2 and number 4 is our start signal. Okay, that's plus 24 volts digital signal, again coming in from our PLC. So when we're in local, this switch opens up. We don't see 24 volts on contact digital contact number 5, okay, which means this will work. We will be able to start the drive from our local faceplate, and we can stop the drive from our local faceplate. Okay, and this will all work. The potentiometer will speed up the drive. We'll slow down the drive, and our start and stop buttons here work. Okay, so what we did then is we wired this up. So this switch closes, goes into digital input number 5, and then now this is disabled because it's looking for start signal number 2. It's start source number 2. Now where does that come from? That comes from our PLC. Okay, and so all that will come from the PLC. And so if you've been in PLC's class, you've done this before, not so much wiring it up to a drive, but you've done this by wiring it up to a pilot light. And so if we just pull this screen on our PLC, it's kind of in the shadow, so it's a little bit dark. But this is where our speed signal comes from, which is right here, this analog output. Okay, these two wires are connected into 13 and 14 on the drive. Our start signal comes from digital input 1, which you can see by this pilot light here. Whenever this comes on, the drive will start. Okay, so we're in remote mode, and so if I push this button, you can see and hear the drive and the motor start. The motor is now running, and the drive's running. You can see the pilot light on there. Okay, now since this is in remote mode, I cannot change the speed using this potentiometer anymore. The only way I can change the speed is with the PLC. So I change the speed with the PLC just like an operator would do. It's set 75% now. If I want to slow it down, I give it a signal of 25%, and that'll slow it down. Okay, so what that did is that took this signal here, and it went down to 2.5 volts because it's a 0 to 10 volt range, and it went down to 2.5 volts. which then slowed the drive down. And if I want to speed it up, I can then speed it up to 100% to give it full speed to the motor. Our full speed of the motor is going to be 60 hertz. Okay, so we can watch this ramp up to 60 hertz. Okay, and so I just slowed it down using the PLC because I'm in remote mode. Right? Now, notice what I just did there. I'm in remote mode. This start button will not work. The only way for me to start it is from the PLC. But what did I just do? I just stopped it from the local faceplate. When we're in remote mode, for most drives, as an added safety feature, you can always stop them. Okay, this button, this stop button, whether in your local remote or your remote mode, this stop button will still work. So I'll show you it again. Start the drive remotely using the PLC. I am in remote mode. Okay, I cannot change the speed by changing the potentiometer because I'm in remote mode. Okay, but I can still stop it. Okay, that stop button works. I cannot start it up again because I'm in remote mode. But as an added safety feature, most drives will allow you to still stop it even though you're in what we consider remote mode. Okay, notice what this type of signal is. Okay, this signal is considered a two-wire signal. Okay, that means that the signal has to come in from the PLC, the start signal comes in from the PLC and it stays on. This is not like a push button that's just momentary. So whenever I start this drive, notice that LED comes on and that LED stays on. Okay, this LED 1 is what we're looking at. So that's a start and run signal. There's one pair of wires that go from that digital output of the PLC going into the drive. There's no other command that tells it to stop. What tells it to stop is when that signal goes away. So when this LED goes off and I tell it to stop, that's when the drive will stop. There's no separate stop signal. Okay, that's when we're dealing with PLCs. If we're dealing with push buttons, if you remember from motor controls class, you're going to have two different ones to be able to do that. Okay, so it's working the way we want it to. So the next thing we want to do is we want to go down and be able to answer these questions. Okay, so after we wire the drive, we should start and run it in local mode, which we already did, but we'll do again as a refresher. So we're in local mode here. So if I start it, I can start it from the local push button here. And I want to speed it all the way up. And we know what frequency does the drive run at full speed. The frequency is right here. It's right at 60 hertz. That's the frequency, 60 hertz. What relays or terminals are connected to the pilot light? That's R1 and R10. Okay. What voltage is required to pilot light? That pilot light is a 110 volt pilot light. So notice on our wiring diagram, everything else, the speed signal, the start run, the local remote is all 24 volt DC. But the pilot light does not go through any of that. It comes through here through R1 and R10. That is all 110 volt AC pilot light. So it doesn't use any of the digital terminals on the block. It uses these relay terminals up here, which as you can see are kind of set off a little bit. And if I go down to this zoomed in view, you can see that these are kind of set off a little bit. Okay, that's because these are relay terminals. Right, everything else in here is going to be a 10 volt or a 24 volt signal. So the voltage required to PLC is 110 volts AC. Now we turned off the drive and we switch it into remote mode, and then we want to be able to start and run it again. So whenever we switch into remote mode, what contact terminal number pulls in 24 volts? That's contact terminal number 5. Okay, contact terminal number 5 will pull in 24 volts, putting us into remote mode. Okay, we can see it on the wiring diagram here. 11 has plus 24 volts on it, comes down, this switch closes, putting plus 24 volts on that terminal number 5. Okay, when the drive is in remote mode, is the start button on the faceplate disabled? We're in remote mode now. I cannot start it. So yes, number 5 is yes, the start button is disabled. Now, is the stop button disabled? If I start it remotely from the PLC, the stop button will still work. Okay, I can still stop it right here. Okay, so is the stop button disabled? No, it is not disabled. It's still active. And then what is the range of the signal coming from the PLC going into the drive? In this case, it's a 0 to 10 volt signal. Okay. Other signal that we could use is either negative 10 to positive 10 volts, or a very common signal that we see a lot is 4 to 20 milliamps. Okay, 4 to 20 milliamps. And it's something as simple as, for this particular drive, it's something as simple as switching this wire from terminal 13 into terminal 15. Okay, that's all we have to do for this particular model is pull this red wire off of here and put it in number 15 down here. And on the drives in a previous lab, that's what this selector switch was for. Okay, this selector switch up here was VI switch was telling us, what type of a signal do we have coming in for our remote speed signal? I for milliamps or V for voltage. Okay, so that's how that one is done. This one, you just simply land a wire on a different terminal, okay, to get that 4 to 20 or 0 to 10 volt signal. Number 9 asks, if the drive is running in remote mode and power is lost to the PLC, will the drive keep running indefinitely or will it stop? So basically what's going to happen if we don't give it a stop command, right? So we're running and we're in remote mode now. So you can see the motor is running. Okay, the drive is running. We're about 50% speed here. And so what's going to happen if this PLC loses power, but the drive doesn't? Well, if the PLC loses power, what should happen is this signal here should go away because the PLC doesn't have any power, so it can't give it a signal output, which is just the same as telling it to stop in remote mode. And so what we should expect to see is simply to have the motor stop. Right? So we can kill the power to the PLC, which we just did there. You notice the motor stopped running. The drive is still working. Okay? The drive is still up and running and going. Okay? But the motor is not running. Okay? So if we wanted to get the drive up and running to fix this problem with the PLC being out, we can simply put it back in local mode, ignore the PLC, just use our push buttons here on the faceplate. Okay? And the final question for the lab, why are variable speed drives becoming more popular versus typical control valves? Main reason is cost savings, energy savings. So drives are becoming cheaper and cheaper as they are more and more mass produced. More and more companies are making them, making it more competitive, driving the cost of the drives down. What happens when we want to control the flow of a fan or a pump or different things like that is we can control the actual speed of the actual motor turning, which can reduce power costs. Okay, it can reduce utility costs. Okay, if we change the frequency of that motor, it's going to slow it down, be able to control it, which is going to save us in energy costs. Okay, control valves, typical control valves that we looked at for the first 8 weeks, do not save us on energy costs. Okay, they put restrictions in the pipe, which do not, or the ducts, which do not save us on energy costs, but putting in the drives will save us on energy costs. That's the main, one of the main features of them. Some other more programming and versatility to them, more options than what a control valve would have. But one of the main reasons why they're becoming more and more popular is because of the energy savings that they have. All right, so that should be it. You should be able to answer all the questions and turn it in on Blackboard.